Welcome everyone. I'm excited to kick off our presentation with an overview of duct systems. Today, we'll explore the main air distribution systems that keep buildings comfortable and efficient. The title of our session is Duct System Overview, and we'll be looking at different types like rectangular, circular, spiral, flexible, and fabric ducts. We'll also take a visual tour through a 3D rivet view, showing how the air flows from the AHU to the main duct, then branching out to diffusers. Plus, we'll identify key icons representing supply, return, exhaust, fresh air, and diffusers. So, let's get started and dive into how these systems work together to create effective indoor environments. Let's take a closer look at duct classification and the materials used. When we talk about materials, you'll often hear about galvanized iron, aluminum, stainless steel, pre-insulated ducts, and flexible ducts. Each of these has specific applications depending on the requirements of the system. Now, moving on to pressure classes, which are crucial for understanding how ducts are designed to handle different air pressures. We categorize them into low, medium, and high-pressure ducts. Low-pressure ducts operate up to 750 pascals. Medium-pressure ducts handle between 751 and 1500 pascals, and high-pressure ducts are designed for anything above 1500 pascals. An important concept here is the pressure formula, which helps us understand how pressure relates to air velocity and density. The formula is P equals rho times V squared over 2. To make this more tangible, consider an example. If the air density is 1.2 kilograms per cubic meter and the velocity is 8 meters per second, plugging these into the formula gives us a pressure of about 38 pascals. Understanding these classifications and the principles behind pressure helps us select the right duct type for specific applications, ensuring efficiency and safety in our ventilation systems. Let's take a closer look at duct sizing using the velocity method. The key formulas here are quite straightforward. First, we have flow equals area times velocity. This means that if you know the flow rate and the velocity, you can find the cross-sectional area of the duct. Conversely, if you know the flow and the area, you can determine the velocity. The second formula is simply rearranging that. Area equals flow divided by velocity. This is very useful when you're designing or adjusting duct sizes to ensure proper airflow. Now, let's walk through an example to make this clearer. Suppose we have a flow rate of 1.8 cubic meters per second, and we want a velocity of 6 meters per second. Using the formula, the area would be flow divided by velocity, which gives us 0.3 square meters. And when we translate that to a practical duct size, it's approximately 600 by 500 millimeters. This helps us visualize the actual duct dimensions needed to achieve the desired airflow while maintaining the proper velocity. So, in the context of our overall design, understanding and applying these formulas ensures we select ducts that optimize airflow, reduce noise, and improve system efficiency. Let's talk about duct sizing using the friction loss method. The key here is understanding the formula. Delta per L equals F times rho times V squared divided by 2 times D. This formula helps us calculate the pressure loss due to friction along the duct. Now, the design rule to keep in mind is usually 1 pascal per meter, which serves as a practical guideline for acceptable pressure drop. For example, if we take typical values like a friction factor F of 0.02, air density rho of 1.2 kilograms per cubic meter, a velocity V of 6 meters per second, and a duct diameter D of 0.5 meters. Plugging these into the formula gives us a pressure loss of approximately 0.86 pascals per meter. This method is very useful because it provides a clear way to estimate how much pressure is lost due to friction, so we can properly size our ducts and ensure efficient airflow without oversizing or undersizing. It ties back to our overall goal of optimizing system performance and energy efficiency. Let's take a closer look at the equivalent diameter when converting from a rectangular to a round shape. The formula we use is D equals 1.3 times the quantity of a times B raised to the power of 0.625, divided by the sum of A and B raised to the power of 0.25. This helps us find a circular diameter that has a similar hydraulic or flow characteristic as the original rectangular shape. For example, if we have a rectangle with a length of 600 millimeters and a width of 400 millimeters, plugging those values into the formula gives us an equivalent diameter of approximately 508 millimeters. Understanding this conversion is important because it allows us to compare different shapes in a consistent way, especially when designing or analyzing systems where flow behavior is critical. It's a useful tool that ties into the overall theme of accurately representing complex geometries in practical engineering applications. Let's walk through the key points for duct layout and coordination. First, we need to locate the AHU and the main trunk. This is essential because it sets the foundation for the entire duct system. Once we have those in place, the next step is to coordinate with beams and other services. It's crucial to ensure our ducts don't interfere with existing structures or systems, so careful planning here is vital. We also need to keep proper clearance and maintain the correct slope for drainage and airflow efficiency. Missing these details can lead to issues down the line. Lastly, don't forget to add access doors and dampers where necessary. These components are important for maintenance and controlling airflow. On this slide, you'll see a visual overlay combining a 3D model with a 2D plan, which helps us visualize the layout clearly. Overall, effective duct layout and coordination are about careful planning, respecting structural elements, and ensuring accessibility, all key to a successful HVAC installation. Now, let's talk about the duct installation process. First, it's crucial to verify the hanger spacing according to SMACNA standards. This ensures the ducts are properly supported and reduces the risk of sagging or damage over time. Next, we need to seal all joints using mastic or tape. This step is vital because it prevents air leaks, which can compromise the system's efficiency. After sealing, the installation of insulation and labels comes next. Insulation helps with thermal performance, and labels are important for future maintenance or troubleshooting. Finally, before closing up the ceiling, always test for leakage. Checking for leaks at this stage allows us to catch any issues early, saving time and effort later. By following these key points, we ensure a reliable, efficient duct system that aligns with our overall goal of quality and performance. Now, let's move on to the section on testing, balancing, and commissioning. Here, understanding some key formulas is essential. First, we have CFM, which stands for cubic feet per minute, and it can be calculated by multiplying the velocity of the airflow by the cross-sectional area. Conversely, if you know the CFM and the area, you can find the velocity by dividing the CFM by the area. For example, if the velocity is 4 meters per second and the area is 0.2 square meters, then the CFM would be 0.8 cubic meters per second, which is equivalent to 800 liters per second. This kind of calculation helps us ensure the system is operating correctly. Another critical point is leakage testing. The standard limit for air loss is less than or equal to 5%, according to DW 143. Maintaining this limit ensures energy efficiency and proper system performance. Remember, these formulas and limits are vital tools in our testing and balancing process, making sure everything runs smoothly and efficiently, aligning with our overall goal of optimal system performance. Let's now talk about documentation and submittal, which are crucial steps in ensuring everything is properly documented and approved. First, we need to include shop drawings, which consist of both 2D plans and 3D views. These drawings give a clear visual of the installation and help us visualize the project more comprehensively. Next, the pressure test report is essential to verify that the system is sealed and functioning correctly under pressure. We also need the air balancing data sheet, which confirms that the airflow has been properly balanced for optimal performance. Material approval, or MAR, is another key document. This confirms that all materials used meet project specifications and standards. Lastly, compliance and as-built drawings are vital. They ensure that the actual installation matches the approved plans and standards, and they serve as a reference for future maintenance or inspections. All of these documents collectively ensure that the project is transparent, compliant, and ready for review, aligning with our overall goal of quality and precision in every step. Let's take a moment to review the key reference standards that guide our work. First, we have SMACNA 208, which focuses on duct construction. This standard ensures that our duct systems are built to last, are safe, and perform efficiently. Next is ASHRAE 62.1, which sets the benchmarks for proper ventilation. Proper ventilation is crucial for indoor air quality and occupant comfort. Then there's ASHRAE 90.1, which emphasizes energy efficiency. Following these standards helps us design systems that are not only effective, but also sustainable. We also refer to SBC 501, the Saudi building code specific to HVAC, ensuring our designs comply with local regulations and requirements. Lastly, DW 143 relates to duct testing, which is essential for verifying that our systems operate as intended and meet quality standards. Connecting all these standards to our overall theme, they serve as the foundation for safe, efficient, and compliant HVAC systems that deliver comfort and performance in every project.